Lesson 10.5 is about base E and natural logarithms. Before we get there, though, we're going to start looking at kind of a real-life application of logarithms. And one form is finding compound interest. Now, compound interest is kind of a fancy word for what happens to your money in the bank. So in this case, A, this value here, is the final amount. So how much you get after you've invested for so much money for so long. P is your principal amount. It's how much you started with, how much you put in there. So if I put in $100 and I wait for so long, then A, my final, is what I get out, is how much I'm getting back. And it's nice to know that, so you know over time how much money you should have in the bank if you just put some money in there and leave it be. R is your rate of interest as a decimal. So if you said it's growing by a half, your R here would be 0.5. 50% is 0.5. 60% is 0.6, and so on. N is the number of times the interest is compounded per year. And by that we mean if it's compounded every year, then you only check it one time. So you just put a 1 there. If you check it twice a year, it would be 2. That would be semi-annually. And T is your time in years, how long you had it kept in there. And actually, I guess that N shows up twice, and there and there. So let's see exactly how this bank example plays out. Assume you invest $1 for 1 year at a rate of 100%. So at the end of the year, it should grow by 100%. It's its growth rate, which means our R is 100% or 1. 100% is the same as a decimal as 1. So our principal at P is 1. That's how much we're starting with. Our rate of growth is 1. And our T is 1 year. T equals 1. I guess I should have underlined investment $1. Substituting them into our equation, then we get, essentially it comes out to A equals 1 plus 1 over n to the n power. Because we said R was 1 and T was 1. And our principal actually was even 1. So it's just a lot of 1 timesing a lot. So this then becomes our table. This is how it looks. Again, checking annually once a year means we're only checking 1. So plugging 1 in for our n value here, puts it here and here. So that would actually be 1 plus 1 over 1 is 1. So 1 plus 1 is 2 to the 1th power. So after a year, we'd have $2. If you put in $1 and it grows by 100% and they check it once a year, you get $2 total. So you grew by $1. So let's say that they check it semi-annually. That means it was checked twice, once at the middle and once at the end probably. So we would plug 2 in at our n value at the bottom here and for our exponent. 1 plus 1/2 would be 1.5 to the 2nd power or squared. So at the end of that year, you would actually have 2.5. So it's actually better if they check it more times. So let's say they checked it quarterly. So every 3rd month or so, they would check it. It was checked 4 times the year. So it'd be 1 plus 1/4 to the 4th power. Well, 1 plus 1/4 is 1.25 to the 4th power. So that would actually come out to 2.4414 and some other numbers there. So you'd have about $2.44, which again is more than that $2.25 if they checked it twice. So again, the more they check it, the better. Monthly means they would be checking it 12 times a year. There are 12 months. So that one would actually look like 1 plus 1 over 12 to the 12th power. Check that in your calculator, plug that all out, and that is going to get you 2.6130 and some other values there. So again, about $2.61, which is more than that 2.44 or $2.44. So again, check it more, you get more money. Weekly, there's 52 weeks, so they check it 52 times. 1 plus 1 over 52 to the 52 power. That would actually get us 2.6925 and some more. So about $2.69, getting more. Daily is 365 times 1 plus 1 over 365 to the 365th power. So we're getting a little more here. 27146 and some change hourly. So they checked it every hour. Well, that's 365 days times 24 hours in a day. 8,765 hours in a year. So 1 plus 1 over 8765 to the 765 power. Getting to be some big numbers. So that one didn't grow by a ton, but it's still bigger than the one before. What if they checked it every single minute? You had somebody on it at all times, 5,000 or 525,600 minutes in a year, just like rent. Thanks, hipsters. So that one would be 1 plus 1 over, I'm just going to say that rent value, whatever they sing about minutes in a year. That would come out to 2.7182 and some change. Same thing here. There's how many seconds there are in a year. I'm not even going to write that out, but we know it would be 1 plus 1 over whatever this value is, a lot, to that power, whatever that is. It's going to come to 2.7182 something. Again, it's not much, but it's going to be bigger than what it was before. So if n continued to increase even larger, so meaning you had them check your account more and more throughout the year. Let's say they checked it literally every single moment, so checking it continuously, then this number over here would approach E. E is this number here. It is considered an irrational number. And it's also considered the natural growth number. It's the second most common irrational number next to the number pi. Remember, pi was an irrational number. That is the ratio of a circle's diameter to its circumference. Well, E is, again, another irrational number that has to do with natural growth. So E is referred to as the natural number, E. An exponential function with E is your growth factor, is known as your natural exponential function. So we could say then as well that the natural log, which is also, you'll see this button on your calculator, ln instead of log. So there's log, which would be log base 10, and there's the button ln, which, as you can see over here, that's the same as saying log base e, is this, ln function. So the natural log is a logarithm with base being the number e. So if we needed to approximate the following values to 4 decimal places, again, you just plug these right into your calculator. So if we did e to the 0.5, that one's going to come out to approximately 1.649. E to the -8 would be approximately, I do need to do that one, be approximately 0.00034. Or, in scientific notation, we'd write it as 3.355 times 10 to the -4th and bring it over. It looks a little bit different because it was rounded differently. Again, using our calculator, we just hit the ln button, do ln of 3, which would be approximately 1.099, and punch that button ln of 1/4 would be approximately -1.3863. So those are some approximation and solving using our calculator. So if we wanted to write equivalent exponential or logarithmic equations, well, if we have this e to the x equals 23, well, again, that'd be like saying log base e of answer 23 equals x. But remember, log base e, we just call that ln. So we'd say ln 23 equals x. That's how we'd change that. So similarly over here, this one would just mean that ln of 6 equals x. Anytime we have e to an exponent equals a number, it would just be ln of that number equals x. Now over here, if we had ln of x equals 1.2528, that would be like saying, remember ln is log base e of x equals 2.5280. Well, again, if we wanted to rewrite this into exponential form, this would be like saying e to the 1.2528 equals x. So this is our exponential form that we're looking for. In this last one, notice how we went from ln x to 1.2528 is just e to the 1.2528 equals x. We'll do the same thing here. We'll just say then that e to the 2.25 equals x. Cut out that middleman of doing this log power. Perfect. Now moving on. If we want to evaluate what each of these things mean, well, first off, let's look at this little piece up here, this ln 21. What exactly is that saying? What does that mean? Well, it means that the log base e of 21 is some number. These are the same thing. Log base e of 21 is x. And we don't know exactly what that x means or what it is. We could plug it into our calculator and find it out, but let's just think of this intuitively. And we know that if we change this to an exponential form, we would say then that e to that number x is going to be 21. So, if ln of 21 equals x, essentially then we're saying e to the ln 21 is the same as saying e to the x. And we already knew from down here, e to the x equals 21. So this piece, e to the ln 21, equals 21. So anytime that we have e to the ln power, we can essentially just cross out that e and ln, and it'll leave us with 21. So let's try that over here. E to the ln, just cross it off, and all we're left with is 7. Nice and easy. Same thing here. What does ln of e to the power of x plus 3 mean? Well, again, ln is like a log base e of e to the power of x plus 3. So what it's saying is this value, let's set it equal to h. So if we write it in this form, what that's saying is e to the h power equals e to the x plus 3. Well, notice how we have the same base in each time. It's e. So we can just get rid of that and say that h equals x plus 3. So if h equals x plus 3, then this whole value here just equals x plus 3. So again, it's just like canceling out the ln with that e. So let's do that over here. We have ln of e to the 5x minus 7. Cancel those out, and we're left with 5x minus 7. Nice, quick, easy properties to help us with those logarithms. So if we needed to solve some logarithmic equations here, start out just like any other equation. Get it down to a simplified version of x as you can get. So what I would probably do here is get rid of that 4 from both sides, just subtract it out. And we'd have 3e to the negative 2x equals 6. Well, now we can divide both sides by 3, and we would get e to the negative 2x equals 2. Now, we may not know what to do from here, but we know from those properties, we can just take the ln of both sides to get rid of that e. So if we do ln over here and ln over here, these will cancel out. So we'd have negative 2x equals ln 2. Now if we divide both sides by negative 2, we would get x equals, ln 2 over negative 2. And solving that on our calculator would leave us with x equals negative 3.47. Nice and easy. So if we had, again, started with this equation, we can just subtract 5 from both sides. 2e to the negative 2x equals 10. Divide both sides by 2, and we would get e to the negative 2x equals 5. Take the ln of both sides, cancels out. ln negative 2x equals ln of 5. Divide both sides by negative 2, x equals ln 5 over negative 2. And so on our calculators, that would show that x equals negative 0.805. Nice and easy. Last two here. If we have ln 5x equals 4, we'll use our properties again and just do, we'll take both sides to the e power, or e to that power, should I say. So e to the ln 5x equals e to the 4th power. So essentially we're just canceling those out. If that was kind of weird for you, think about this. ln of something is the same as log base e of something. So log base e of 5 to the x equals 4 is what that thing is saying. So we would change it then to 5x equals e to the 4th power, which is what we're saying here. So either way, it helps us get to that same, to this value, where we say 5x equals e to the 4th. Now from here, solving for x, we can just divide both sides by 5. X equals e to the 4th over 5. And we just plug that into our calculator to determine that x equals 10.9196. Perfect. And for this last one, we have inequality. So again, we do the same thing we would do with any equation, just making sure to follow the properties of inequalities. So I would do e to the power of both of these. E to the ln x minus 1 is greater than e to the negative 2. That makes these cross out, so we just have x minus 1 is greater than e to the negative 2. Add 1 to both sides, and we would get x is greater than, where am I? It's greater than e to the negative 2 plus 1. So from our calculator, this would say that x is greater than 1.1353. So again, those are some more properties of logarithms, specifically e, the natural log. So make sure we're asking any questions, otherwise stay golden.